Thank you. Thanks very much for the introduction. So, our work is focused on caustics, and this being the Eurographic Symposium and rendering, I don't think I have to introduce caustics to you. But just in case it's what you see on those images. It's light being focused by specular interfaces, either refractive or reflective, and that's basically a lot of radiance concentrated on a very small space. And the caustics have two key characteristics that make them interesting as a research topic. One, they look beautiful, and two, they are very difficult to compute with regular path tracing. In recent years, for some definition of recent, there's been a lot of work on the manifold approach. This is just key papers in the previous work. If you want an extended version of the previous work, I'll refer you to the paper. But the common idea behind in this line of research is that caustics are basically the zeros of an objective function, and you use the Newton-Raphson method to find those zeros. So I'm gonna go back a level and redefine next event estimation, which you've already heard about in the previous talks, in a very schematic way, very hand-waving way. In path tracing, you're tracing a path to the scene, and this path is bouncing on the surfaces, and you compute the reflected direction. And the idea is that the last point on that path, you connect it directly to the light source, which gives you the direct lighting at that point. And it's very easy to do, and it greatly reduces the variance and accelerates convergence in your scenes. No, that works well, but what happens if you have a specular interface? And you've probably had this experience where you have a beautiful kitchen scene and you suddenly replace one of the cupboard doors with a glass door, and suddenly everything gets noisy in the scene. Because next event estimation doesn't work through a specular interface. Hence the idea of manifold next event estimation, where you find the point on the specular surface that connects to the light source. And the key thing is, because it's a specular surface, there's only one point. And I'm not going to go into a deep explanation about all the previous research of manifold next event estimation. But the key idea is you go back to a problem you know how to solve. So you define a function such that for the zero of that function, you have a path that connects to the light source. And that can either be the half vector function, which you have on the left, or the angle in spherical coordinate between the reflected vector and the path connecting to the light source. Or it could even be another function we haven't found yet. Anyway, you're back to a problem you know how to solve, finding the zeros of a function. And the Newton-Raphson method is extremely efficient here. And I'm, spoiler alert, it's probably the most efficient method. The only problem of the Newton-Raphson method is the code complexity. So because you have to compute derivative, which implies path derivatives, which is a multi-dimensional derivative. So you have to invert that, which means inverse of the matrix. Sometimes the matrix is not square, so you revert to the pseudo-inverse. You have to apply the derivatives to the path, and so on. If the main feature in your scene is caustics, then the Newton-Raphson method is definitely worth it. If you don't have that many caustics, then maybe you will be interested in this talk. So our contribution is manifold next event estimation without path derivative. We're going to keep a lot of the existing methods. So we have the same objective functions, and we're just going to find the zero of the objective function using the Nelder-Mean method instead of the Newton-Raphson method. The problem also is that the Nelder-Mean method is for finding the local minimum of a function, and instead of the zeros, so we just take the norm of the objective function, and then the zero is a minimum. I'm going now to explain a bit shortly what's the Nelder-Mean method. It's a generic method to find the local minimum of of a function in dimension D. And it works by maintaining a simplex of D plus 1 sample points, and at each step, you update the simplex to converge towards the local minimum. So for an example here in dimension 1, we have a simplex of 2 points, and we take the, So my examples are in dimension 1. Neldermin method works in any dimension D. And the first thing it does is to find in what direction you're going to update your simplex. And it does that by taking the point with the largest value, which is the point you want to move away from, and takes the centroid of all the other points. So by magic, your D-dimensional problem has just been changed into a one-dimensional problem. So in my case, that's xd and y, which is the centroid of all the other points. And I take the symmetric of xd with respect to y, and that xr for reflected, and I compute the value of the function. Now, if f of xr is the smallest value so far, it's smaller than all the other sample points, then obviously it's a good direction to go with. So I try to go even further, and I try xe for extended, which is going even further in the same direction. And if the new value of the function is even better than anything else, that's the point I'm going to use and replace the old point xd with xe. If it's not that better, then I'm going to use xr. And similarly, if xr is better than the second worst point, I'm also going to keep xr. It's a good direction. Let's keep it. So that's the first case, and that's the second case. Now, obviously, if xr is worse, is the worst value so far, then it's not the right direction. We went too far, so we're going backwards. So try to go in the direction between xd and y, but in the other direction, so in the middle between xd and y, and we check if that's a good direction. If it's a good direction, we keep it, and that's our new simplex. Oops, sorry, a bit too fast. And that's our new simplex. And there are a third possible case. If xr happens to be between the worst and the second worst point, again, it's a good direction, but xr was probably too far, so we compute xq, which would be the middle between y and xr. And again, we operate tests based on the value of xq. And in all those cases, there's a backup solution. If none of your sample points work, you simply shrink the simplex around the best point, which gives you a smaller sample. And since x0 is the best point, it's probably a good area to look back. So that's Nelder-Mini method in 25 words or less. And now, how do we do in practice? So as I say, this method integrates within the next event estimation system. So first, we trace array through the scene. We'll have this point P, which is the last point of the path. And we want to connect it to the light source through specular reflection. This is where specular manifold sampling would first choose a sample point on the surface and then do a Newton-Raphson descent to get to the actual path. Since we have a simplex method, we start by picking up a simplex. So we pick 3 random points on the surface, and that gives us the starting simplex. And from there, we apply the Nelder-Mini method, so that updates the simplex to a different simplex, smaller, and we keep doing it, and the colors correspond to the error scheme on the right, so you can see that I'm gradually improving the value of my sample, and after some time, I converge to a small triangle which has an acceptable value, and I take that as my point. So now I take it as my point, I compute, I connect it P through that point to the light source, I compute the contribution, and I have my value at point P, my radiance value at point P. Now, that was the basic idea, but there are a few things. First, we don't have a parameterization of our surfaces. They're just triangle soups. So when I say we take a new point based on the symmetric between xd and y, that gives me a point that's basically floating in space. So I back project it to the surface using raycasting as one does, and you have the idea here. This being an iterative search function, we stop the search if the value of our objective function falls below a certain threshold, if the size of the triangle is too small, or after a certain number of iterations. I don't suppose you're surprised by those conditions. We also introduce a preliminary rejection if the search will not converge, and that is based on the fact that Nelder-Mead converges to a local minimum. So if we trace our objective function, we sometimes find something like that. And looking at the curve, it's obvious that we are not going to converge to a zero of the function, but only to a local minimum, and that's not interesting. And since the curve is mostly convex, we use the tangent to estimate that this is not going to be an interesting set, and that gives us a preliminary rejection, which makes us gain some time. There is a key point in the paper of Zeltner and colleagues on specular manifold samplings, is that you can have multiple paths connecting the same point to the light source. In order to have a valid estimate, you need to know the probability of the path you just found, so you have to actually run multiple search to check if this is the most obvious path or actually a rare path that you found by chances. So Zeltner does that by running multiple search with different starting points. We do the same thing, except we run multiple search with different starting simplexes. Okay, now the question is, does it work? So I've got good news and I've got bad news. If you look at the images, you see obviously the good news, which is the images look identical, or actually very close. Probably not seeing any difference. I can tell you I don't see any difference. So that's good. We get the same results. If you look below the images, you can see the bad news, which is it's 2 times slower. The reason being that there's a lot more iterations. We take around 20 to 50 iterations to converge. So even if each of them is cheaper, it's still globally more expensive. We do get a few more results. The digit below is the convergence rate, that how many times your search actually converges to a solution, but that's not extremely significant in my view. So to express a bit more the difference between the two images, this is the similarity metric with a reference image. And even looking at the similarity metric, you're not going to see a lot of differences, which is normal. I mean, that's the good thing about this algorithm. It does give you the same results. With different scenes, you get the same results, like we find the same caustics. The images look the same, but the computation time is multiplied by 2.5, which is not satisfying. Convergence rate is slightly larger, but again, not significantly larger. And the similarity matrix is again going to tell you the same story, which is basically we found the same caustics. And the same story with our third test scene, which is a specular Stanford bunny. Same quality, same results, and so on. So, in conclusion, we just showed a method to compute the manifold next event estimation without derivatives using the Nelder-Mead method. It's slower than the Newton-Raphson method, but it has the same convergence rate. And the key advantage in our view is that it will result into a smaller code base. So if you want to add caustics to your favorite path tracing without expanding a larger code base, you now can. In future work, we want to work on extension to multiple specular interfaces, refraction interfaces, and also combine it with previous work of ours that introduced the coplanarity constraint, which restrains the search for path for caustics, and potentially application of the Neldering method to other problems of finding local minima. Thank you very much.